Welcome back to another tutorial, Machine Learning Decision Trees 2021. I will show you how to use them in Python, how to predict with them, how to plot the actual tree, and everything you can do with them. In the end, we will also look at a theory lesson about how they are constructed. So if you're only interested in that, also skip right to that point. Let's jump right into Google Colab. I noted really everything that could be potentially interesting to you when you want to learn about decision trees, how to train them, and yeah, let's jump right in. First thing we need to do is import all the classes. Today we'll be mostly working with pandas as the underlying data frame engine. We'll work a lot with sklearn. So sklearn, for those that are not familiar with it, it's also called scikit-learn. It is really one of the most used machine learning libraries, especially for the more classical approaches such as decision trees. We will load some data set, we will train test split, and we'll classify what we've actually did. I'll also show you how to store them in case you want to reuse them somewhere, and a little bit of plotting from Matplotlib's side. First thing we do, we load the dataset. So we will be using the wine dataset from sklearn because it's pretty simple to load up and you don't need to find a dataset and import it somewhere. First thing we'll do, we'll build a data frame from it. Pretty straightforward, really. Just give it the names. Then we'll do a train test split at 80% and 20%. This is just a handy little function from sklearn that you can use to get that right out. So let's have a look at the data. And this has a lot of features. So what are we trying to do today? We are trying to predict whether a wine is in one of these classes, so 0, 1, and 2. And to do this, we are given a shit ton of very complicated feature names that I have absolutely no clue of what they mean. But really, it's chemistry, so how hard can it be? Yeah. How to initialize a decision tree? The first thing you need to do is just call tree.decisionTreeClassifier. You can give there a lot of parameters. So if you go into the function here, actually, you can see that they have some fancy parameters that you can use. I will not go too deep into them, but just such that you know there is a lot you can tune around with. Next thing is fitting. So this is the actual training process. How do we actually train a decision tree? First off, we just give it the train labels and the train features. So how do you do this in pandas? You just give it the feature names. As you may remember, up here we defined them. So these are just these columns, and the label is this column here, this aspect of the data frame, and in the other one we cut this aspect of the data frame. So this column versus all of these. Once you've actually fitted this, you can see what a decision tree is, and we're already here. So wasn't that easy? Really, this is a decision tree, and that's all you need to do to get one. What is a decision tree? A decision tree really is, as the name suggests, a tree that in comes a number of features. So here, let's say this sample come in, and the first thing we look at is really, is the color intensity bigger than 3.9 color intensity, where is it here? So this particular example will go left because it is less than this number. Then you look at the next sample and so on, and you just follow the tree until you've hit a so-called pure leaf. So what is a pure leaf? A pure leaf is a leaf where there is only one class left. Here we see, for example, value. We see that here are only 51 of the samples that we trained on will be classified as class 1. Here, for example, we see there is one class of class 0. So this leaf is pure, this leaf is pure, this leaf is pure, and so on. Just basically the last node. And in between we have these so-called impure nodes. An impure node is really where the actual decision is taken. And you just follow them down the line until you get to a pure node, and this is how you would predict with such a decision tree. And it's really also all that matters. To get a bit more into detail on what you can actually see here, you see here the feature name. If you want to do this yourself, you just have to add these arguments and it will be pretty straightforward. And then you see the decision criterion. So what decision did we take at that point? You see a Gini efficient. We'll get more into this in the theory. You see how many samples. So here we, for example, have 142 samples, and on this branch there will be only 55, and on this branch will be 687. You also see here what kind of classes they are. This is our class distribution. We have 47 from class 0 and so on. And when we split here, we already get a pretty decent split. Here it's only 4 of class 0 and none of class 3. Because apparently class 3 is maybe, I don't know, white wines, let's say. And all the white wines go down here because their color intensity is very different to red wines. This is a decision tree. How would you actually now know how good this decision tree is? To figure out in machine learning how good your model is, you generally call a prediction. So this is how you would predict on values that you have not seen yet. We'll do this on the test set because it's generally a good idea to not test and train on the same data, else you'll just get a super good score and there's no point in doing it. What we get here is our report and how good we were. As we can see with the decision tree alone, we were already pretty damn good. I mean, it's not that hard of a data set. It has only 140 samples, so this is quite reasonable, and you could use this in practice to classify your wines. However, when you're using them in practice, what you'll usually get is less good numbers, and you somehow have to do some feature engineering. So far, we've mostly looked at what decision trees are good at, but really, what are they bad at? I mean, if you imagine here a splitting point, let's say color intensity at 3.9, what you're really doing, you're looking at the line, you're taking some point and you're saying, hey, half of them go right and half of them go left. What they're not so good at is what deep neural networks are pretty damn good at, is like multiplying multiple features together such that you can split also in multi-dimensions, so to say. And really, when you're doing feature engineering, be careful and maybe keep that domain knowledge in your mind and really multiply these numbers or take some thresholds and really be a bit thoughtful about what you're trying to do with this decision tree, because they cannot do everything really. They're just splitting points on a line. To make this a very clear example, I also wanted to put in a way how to actually store and load this model again after you've trained it, so in case you don't want to retrain it every time, and use it in your API and your app. So really, this is the way to do it. And let's now get into a little bit of a limitation of, let's say, decision trees, which is that they will always predict the exact classification. So they will predict either 1, 0, or 2 for the respective classes, and they will not predict the probability. So here we can actually call the function predict probabilities to return the probabilities of our test set, but the result will always be 0, 1. So here we see for class 0, class 2, class 3. And the reason for this is really that decision trees ran at a problem and they split it until it's completely split and all leaves are pure. If you now somehow want to solve that and get actual probabilities, or also get into a bit more sophisticated models, what you can do is actually make a maximum depth. What does this mean? You can give this argument here into the classifier. So when you create the classifier here, you can call here like max depth, right? And say 2. And what that will actually do, it will cut the tree here. So it will not go any further. This helps with overfitting on one side, and on the other side, again, computational complexity. Another probably a bit more smarter way is to actually use random forest. What is a random forest? A random forest is really just a bunch of decision trees. If we would now train 2 of these decision trees, so one's like this and one like this, but on different data, so we say, hey, the first decision tree gets, I don't know, randomly selected 80% of the data, and the other decision tree gets randomly selected 80% of the training data, then we build 2 trees. And what we can then actually do is average the results. We'll give the sample both to tree 1 and to tree 2 and check whether they agree on what category that sample should be in. So imagine 2 trees. You throw the sample in, you go through all the leaves, and at the end here it says class 1 and the other one says class 0. What does that mean? There is a 50% chance that it is in class 1 and there's a 50% chance that it is in class 0. Of course, we're in machine learning, so we scale everything a bit more and we don't do just 2 estimators. But just to highlight here again what I just said, let's train a random forest classifier. Again, this is just a bunch of decision trees. We'll actually build 2 of them. So again, on slightly split different data, and we train. and we predict the probabilities. So what probabilities we get? So here apparently both trees agreed that the sample should be in class 0, but here the samples did not agree, because the first tree thought hey, it's a class 1, and here he said the second tree said, hey, no, it's a class 3. So we get these probabilities. And the classification time here, when it's 50-50, you would just take randomly one of them. In the other cases, it's of course the one both agreed on. Now let's do this with 100 trees. So what does this mean? We just build 100 decision trees and just throw again our features in. We create our tree, we fit and train our tree, and we predict again. We do a classification report, and just to highlight how much better this actually can be, it really depends on the example, and I think for educational purposes it's a lot easier if you think about decision trees, because looking at 100 of these trees, it's not as pretty as here, right? We see 100 are actually a lot better, so it's only 3% in this example, but it can be a lot more in practice if you have a lot more samples and a lot more features. So in practice, really just maybe test around with the decision tree, but then eventually go to the random forest classifier. Unless, of course, the decision tree really already solves the problem very well. Because if you show a diagram like this to someone, they can understand it. It's pretty simple, so we can exactly say why this wine is classified as it is, and everybody understands the reasoning of our machine learning model, which is a big advantage. With 100 trees, it gets a bit harder to explain, let's say. Let's now get into the theory. Why are decision trees made like they are built? So why do we actually select this feature to be at the root? Why do we select this feature to be here? And why do we select exactly the points at which we are splitting? To explain this, we'll make now a very simple data set, and what we're trying to predict actually is whether a user watches a video or not. The features we're using is whether he subscribed to the channel or how many videos he already liked. Intuitively, think about how you would split this now. We see here true, 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 and we see here a lot of true. So intuitively, you would say, hey, this feature is more important and more useful than this feature. Maybe when you split here, how would you do it? Maybe pause the video at this point for a second and just think about it. We'll now get into how decision trees are built and how you can optimally split such an example. Let's first actually fit a tree on this example to see how it would perform. And as our intuition maybe already told us, here just true, false, it's 0, 1, right? So we split at 0.5. This will be true and this will be false. If somebody subscribed, they probably watched the video. If they did not subscribe, they did not watch the video, and then there's one exception case. But why exactly is the tree built exactly like it is? Why do we select the feature subscribed first, and how do we know that we have to split it 3 here? The reason for this is the Gini impurity. So there are generally 2 ways that you can do it. You can either do it with entropy or with Gini impurity. In practice, everyone uses the Gini impurity, so we'll just look at this one. They also work pretty much the same. This looks now like a lot of code and very complicated, but trust me, it's really simple in practice. What we are looking at when we look at the tree, we basically try every possible feature, and for numerical values like here, we test all values that could possibly make sense. And then we look at the so-called Gini score. The higher the Gini score is, the better the point is to use as a splitting point for a decision tree. And this is what we're calculating here for 2 classes. I made it only for 2 classes, so it's a bit simpler to understand, but it really is not much more difficult for multiple classes. To make the definition now a bit more simple, we'll always treat left as less, and we'll always treat right as more. Also, false will always be on the left, and on the right side of the tree will always be true. So when you go down this road, this is always less right here, and this is always more. What we need now to calculate this is the count watched videos left. So the count of samples that are less and evaluate to the target true. Also, we need the count watched video right now, the count of samples that are more, and evaluate to the target true. So for an example, count watched video right is really just when you go down here. So somebody that subscribed, how many of them are actually evaluating to true? If we look here, we see we have 3 true samples, and we see 3 of them actually evaluate to true. If we go left, right? We see 3 samples and 3 of them are false, and 2 of them, only 1 of them evaluates to true. So this is the number we need, 1 and 3. What we also need is the count of total values that go left and the count of total values that go right. If we go again here, we see 3 go right and we go 3 go left. I wrote it up pretty extensively. You could also put this into just one line, but I think it's easier to understand like this. So the total count is really just the count of samples from right and left. So really here 3 plus 3, which is also 6 here. And we have the probability of going either right or left. Really, this is just a count of all the nodes in right and left. So this is 3 divided by 6 in the case above. But we also need is the probability of left being true. So really, how many of the samples that we went left are actually evaluating to true. So how many of the people that did not subscribe watched the video. And this is how you can calculate it. Then some fancy math. We take the probabilities of going left, and then we square it, and then we take the other, so the counter probability, which would be the probability of going right, and again square this. This is just the counter probability to this. This is really just some fancy math here to keep the probabilities pretty much at the boundaries. So we see here an x and we see a y, and their values between 0 and 1, and we see when it's good for splitting, basically this score goes up. So at the boundaries, the score is better. One more thing we need to do is actually weighting the probabilities with each other. So we just multiply the probability of going left with the squared class probabilities, as it's called, and we'll get 2 values, which is left and right. Don't worry, I'll explain this in an example below a bit more in detail. And what we'll then get when we add these 2 is the so-called Gini score. There's also a Gini impurity, but this is really not so important for this example. It's just for, completeness. Let's now look at this in a bit more detail and really check this out step by step if you wanted to calculate this by hand. So the first variable we need is count watched videos left node. If we go to the left, how many of the people did actually watch the video? If we go to the left, we see here we have 3 samples that go to the left, but only 1 of them is true. So the number is 1. If we go to the right, so subscribed for the feature subscribe now, right? How many of the people that subscribed actually watched the video? We have 3. The next number we need is the total count of the samples that go left and the total count of the samples that go right, which is 3 in both cases if we split at 0.5. Now for numerical variables, this is a bit more complicated. We also have to find the optimal splitting point. So why do we take here 3 basically and not, 5? I mean, if we look here at the values, we could pretty much take an arbitrary point and split, for example, here at 6.5 on 1.5. Why do we take 3? And the reason the way to find out why that is the case is by first sorting all the values that we have. So we have here the values. We have 1, 2, 4, 5, 6, 7, which if you validate 1, 2, blah, blah, blah. And then we try always the values in between this value and the next value. What would that actually be? This would be 1.5 here, there will be 3 here, this would be 4.5, here would be 5.5, 6.5, and so on. And then we calculate for each of these values the Gini score. We will then take the highest Gini score, and this is our splitting point. Let's now do this for each example. So basically I'll iterate here now through the values. We have here basically always 1 and 2. So the position at so the value at position I and the value at position I.1, which is for the first iteration here 1 and 2. We take the average, which is 1.5, and then we again count all our values basically for the 4 things. So we have here again the amount of videos that are both higher than this average, and the label evaluates to true, so they also watch the video. Then the same thing vice versa, really. Oh, here it actually should be smaller, just saying. Yeah. And then we again have the probabilities that anyway a sample goes either right or left. We throw these 4 values into our function, and what we're getting is here our Gini scores in the first value of the tuple. And if we compare all these values with each other, we see here 0.778 is the best and highest value. So we will split at the feature subscribe at 0.5. Why didn't we take the other value, or why didn't we split at the count liked videos? Because the values are lower. If we would have split there, we would have actually split at 6.5, which may be a bit unintuitive to you. But if we actually just look at this column, we see that if we look at the truths and the falses, here at 6.5, we actually get a good split because we can split off 1 false. We get a not so good score for the other ones. I mean, if we would try at, I don't know, 1.5 here, we would not really split off anything from anything. I mean, here's a 4, so we could maybe split at 4.5 or so, but it's really not that good of a feature, and splitting at 6.5 at least gets us 1 false away. Once we've decided in the first round for our feature subscribed, again because the Gini score is the highest, we can now calculate the values for the next leaf, and we would also do this for this leaf if it was impure, but to make this example simple, we just split here. So to calculate now the values at this point, we have to just really look at the samples where subscribed is false, because we went left and we're only left with 3 samples. So yeah, that's what we have to calculate. Again, this would be the data frame in the left side of the. If we go left, this is the data points that are still round, and to calculate again our values, we can really just calculate exactly the same as we did before, but only with these 3 values this time. And again, if you would intuitively split these 2, where would you split? Probably at 3, right? Because then you get the 1 true value split from the 2 false values. And voila, you have understood how decision trees work. I'm very happy that you watched all the way through. Please like and subscribe. If you have more questions or want to know more about decision trees, random forest, or classical machine learning, let me know in the comments.